All right, today we're diving into one of the most fascinating and, frankly, unpredictable families in the entire periodic table. Group 1, the alkali metals.
So, here's a weird thought for you. What if the most volatile, reactive metals on the planet were also so soft you could slice through them with a regular knife? This strange contradiction is really at the heart of what makes the alkali metals so interesting.
So what's their big secret? Well, it all boils down to one simple thing. They're all members of what I like to call the lone electron club. And trust me, this one fact dictates absolutely everything about them.
Okay, so if you look at the periodic table, you'll find the alkali metals right there, in the very first column on the left, Group 1. This includes some familiar names like lithium, sodium, and potassium, plus their even more reactive cousins further on down.
You see, being in Group 1 means every single one of them has just one electron in its outer shell. Now, atoms want nothing more than to have a full outer shell. That's when they're stable. So these metals are just desperate to get rid of that one lonely electron. And that desperation, right there, is the engine behind all of their extreme reactivity.
And you know what? That one little electron also makes them break pretty much every rule we have for what a typical metal should be like. Let's just compare for a second. When you picture a typical metal, like iron or copper, you're thinking hard, dense, high melting points, right? Well, the alkali metals, they're the complete opposite. They're soft, they have incredibly low density, and their melting points are so low you could almost melt them on a really hot day.
And this all leads to some pretty bizarre properties. I mean, they are literally soft enough to be cut with a butter knife. The first three, lithium, sodium, and potassium, are so light they actually float on water. And while they're super shiny when you first cut them, they tarnish in just seconds because they immediately start reacting with the air, which, by the way, is why you have to store them under oil.
So they seem totally chaotic, right? But here's the catch. For all their wild reactivity, the alkali metals follow a set of beautifully predictable rules as you move down the group.
There are three key trends to know. First, their melting points get lower and lower. Lithium melts at 180 degrees Celsius, but potassium melts at just 63. Second, their density generally increases. But the big one, the most dramatic trend, is that their reactivity just skyrockets as you go down the group.
So why on earth do they get more reactive? Well, it's pretty cool, actually. As you go down the group, the atoms themselves get bigger. This means that single outer electron is getting further and further away from the positive pull of the nucleus. It's also being shielded by all the inner layers of electrons, which makes it incredibly easy for the atom to just give it away.
And this illustrates the idea perfectly. Just compare the small lithium atom to the much larger potassium atom. See how far away that outer electron is in potassium? It's barely hanging on, which means potassium can give it away far more easily than lithium can. And that's what makes it so much more reactive.
Okay, now for the really fun part. Let's actually see how this increasing reactivity plays out in their spectacular and increasingly violent reactions with water.
The basic chemical recipe is always the same. The metal, which we'll just call M here, reacts with water to produce a metal hydroxide, that's an alkaline solution, and a whole bunch of hydrogen gas.
First up is lithium. Since it's the least reactive of the bunch we're looking at, its reaction is relatively calm. It just floats on the surface, fizzes steadily as it produces hydrogen, and kind of scoots around.
Next up, sodium. This is where things really take a leap. The reaction is so much more vigorous that the heat it generates instantly melts the sodium into a little silvery ball, which then darts frantically all across the water's surface.
But potassium, wow. Potassium is the real showstopper. It reacts so violently that the intense heat immediately ignites the hydrogen gas it's producing, and the result? A beautiful and totally iconic lilac-colored flame.
And it isn't just water, by the way. They also react vigorously with elements from Group 7, the halogens. For example, when sodium metal reacts with chlorine gas, they form a simple white crystal, sodium chloride, which you definitely know better as table salt.
Okay, so now that we know the rules of the group, we can do something really powerful. We can basically predict the future. Let's put you in the chemist's seat for a minute.
Based on all the trends we've just uncovered, what can we predict about the properties of rubidium, the next alkali metal right after potassium?
We can see a clear downward trend in the melting point and a dramatic upward trend in reactivity. So what do you think goes into those two empty boxes for rubidium?
Well, if you predicted its melting point would be even lower than potassium's 63 degrees and that its reaction with water would be even more explosive, you are absolutely correct. The pattern holds true, which really just shows the predictive power of the periodic table.
So the most important thing to take away from all this is really simple. Every single one of these properties, getting softer, melting more easily, and becoming astronomically more reactive as you go down the group, it all comes back to that one single, easy-to-lose electron in the outer shell.
And that leaves us with one last provocative thought. We saw potassium burst into a beautiful lilac flame just by touching water. So, if we follow that trend to its logical and, frankly, terrifying conclusion, what do you even begin to imagine happens with francium, the largest and most reactive alkali metal at the very bottom of the group?